Hello, good afternoon, and welcome you to today class in chemistry. This class is solely based on jam past questions and answer. Now, whosoever is watching this video, our aim is for you to score from 200, 300, and above. That is what we wish anybody watching this video, right? So today class we be looking at some questions in chemistry and how we can solve them. Now, I want to start in this way. You are asked to find the percentage of sulfur in sulfur oxide. That is question 1. How do we find the percentage of sulfur in sulfur oxide? Remember in our secondary school classes, we have learned about calculation involving molar masses as well as relative molecular masses of elements. Now, if we are given a compound sulfur oxide, remember this is a compound called sulfur oxide, and we are asked to find the percentage of sulfur here in the compound. Now, for you to find the percentage of sulfur is very simple. We must first remember the mass number of sulfur as well as that of oxygen. Now, how do we determine the mass number of sulfur? Remember, sulfur is number 16, element number 16, which has the atomic mass of 32. Therefore, to find the percentage of sulfur in the compound, we need to find the total percent of the individual elements in the compound. Look at the box. Sulfur will have 1 sulfur here times 32, and we have oxygen 16 as mass number times 1 times 2. So if we sum this, or this and this give us 32 plus 32. So everything is equal to 64%. That is sum of the individual element, or the mass of the individual element give us 64 in all. Now, how we work the percentage of sulfur in this? Percentage of sulfur, percentage by mass of sulfur is going to be the mass of sulfur 32 divided by the total mass 64 times 100%. So if you divide 32 by 64, you are going to have 1 over 2, because 32 cancel 32, 1 cancel 64, 2. So half of 100 will give you 50%. Therefore, the percentage of sulfur in the compound sulfur oxide is equal to 50%, meaning the percentage of oxygen in the compound is also 50% respectively. That is the answer to such a question. It's very simple. Now let's look at the second case before us. In example 2, we are given the mass, a hydrocarbon compound as CH, and the vapor density of that compound is the vapor density per man. So we are asked to find the molecular formula of the compound. If the empirical formula of the compound is given as CH and the vapor density is 39, what will be the molecular formula of such a hydrocarbon? Remember, in our previous video, we said we have 3 formulae in hydrocarbon. which we likely encounter. One, we talks about the empirical formula. Two, we mention molecular formula and structural formula, respectively. So here, the empirical formula is given as CH and the vapor density is 39. What will be the molecular formula of such hydrocarbon? Now follow me as we calculate the molecular formula together. Recall that your molar mass is equals to vapor density times 2. So if the vapor density is given as 39, we are going to have 39 times 2 would give us 78 gram. That is the molar mass of the compound altogether. But remember, we are looking for the molecular formula, and the empirical formula is CH. Now, RAV N is equals to 78. Assuming we don't know the subscripts or the value of L, which will give us the empirical formula of the compound CH. Now, remember that carbon is having the mass number of 12. So we're going to have 12 plus 1, right? 12 plus 1, because of one hydrogen as mass and now only one hydrogen here. Everything gives us 13N is equals to 78. For me, I want to find N divided by 13. 13 go with this. Therefore, your N is equals to 78 divided by 13. 6. So if you divide this by this, it gives you 6. Now, if the value of oil is equals to 6, remember the ion will affect both your carbon and hydrogen. Therefore, your C times C by this will give you 6, and H will also give you this. So the molecular formula of such hydrocarbon is 66H6, and this compound is called benzene, right? That is the molecular formula of what you are asked to find. It's very simple. Now, if you want to do the structure, remember you have 6 carbon and 6 hydrogen. So the structure will look like this. This is hydrogen, 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 respectively. So this is now the empirical formula of benzene. This is the molecular formula of benzene and the structural formula of benzene, respectively. All right. Now we'll be taking the next question. Remember, this is question 2 that we just solved. And we're going to look at the next question. Now, as I read the next question, that is question number 3. It says 200 cent cube of a gas at 25 degrees centigrade exert a pressure of 700 millimeter mercury. Calculate its pressure if its volume increase to 350 at 75 degree centigrade, respectively. Now, remember, whenever a question involves both pressure, volume, and temperature, the one should come to your mind is you are simply talking about the general gas equation, because remember in our previous class we discussed the kinetic theory of gases, and after which we said Robert Boyle, Charles Avogadro, Graham, Joseph Gay-Lussac Jan Dalton. All these chemists that study the behavior of gas, they also established the relationship between the volume of a gas, the pressure of a gas, as well as the temperature of a gas. Now remember that in our previous video we talked about Boyle's law, which states mathematically as V1 P1 is equals to V2 P2. What does that mean? When the volume of a gas increase by 1, the pressure will decrease by 1. When the volume increase by 2, the pressure decrease by 2. Because a Boyle's law, who established the relationship between the volume and the pressure of a gas, states that a given fixed mass of a gas is inversely proportional to its pressure, provided the temperature of that gas is kept constant. So the more your gas increase, the more the pressure will decrease. So the relationship here between the volume and the pressure is in inverse proportion. While in Charles' law, it says the volume of a given mass of a gas is directly proportional to its temperature, provided that the pressure remain constant. Now, Charles also said when the volume of the gas increased by 1, the temperature will also increase by 1 in the same proportion. And when the volume increased by 2, the temperature increased by 2 at the same rate. Now, if we are to combine these two equations together, remember we are going to have now over T1 over T2, and that gives you the general gas equation, which we call GGE, general gas equation. Now let's listen for the question vividly. We are given volume 1, that is V1, as 200 cm cube, while our T1 is equal to 25 degrees centigrade, and our pressure 1, that is P1, is 700 millimeter mercury. Let me read the question. 200 cm cube of a gas at 25 degrees centigrade exert a pressure of 700 millimeter mercury. Full stop. Calculate its pressure. So it means we are looking for P2. P2, that is the variable we actually have to find or to look for. Calculate its pressure if its volume increase to 250 cm cube. Your V2 is 350 cm cube, while our T2 is equal to 75 degree centigrade or Celsius, respectively. Now look up and follow me as we find the new pressure from that question. You are given all the data, your P1, V1, T1, your V2, T2, but P2 is not given. Now look at what happened in this question. The volume of the gas increased from 200 to 350. The temperature also increased from 25 to 75. And the pressure, which is what we're asked to find, is likely to decrease. If this question must obey Boyle's law, because the volume increase, then the pressure must decrease. Now, but before that, the temperature given to you is in degrees centigrade. As such, we must convert it to Kelvin. And converting from centigrade to Kelvin, we always add 273 Kelvin. So if we are given 25, add 25 to this, that gives us we have 298 Kelvin. That is our temperature one. You get solar temperature one, we're not using 25, but we're using 298. You do the same thing to your temperature two, you add 75 to 273, which give us 348 Kelvin. That's all. That is what you must always remember. Whenever the value is in centigrade, we convert it to Kelvin, because the Kelvin is the absolute and the standard unit for a given temperature. Now, let's all remember that our V1 P1 over T1 is equals to V2 P2 all over T2. Remember what is our concern is P2. You need to cross multiply. When you do that, you're going to have V2 P2 and T1 to be equals to V1 P1 T2. What to find is P2. We now divide those side by V2 T1, V2 T1. This and this will take care of themselves. This and this will take care of themselves. Therefore, your new pressure will now be equals to V1 P1 T2 all over V2 T1. Let's substitute the value into the equation such that our P2 now becomes to, remember that V1 is 200. So this is 200 times our P1 700 times T2 348 all over our V2 is 350 times T1 298. Now all you need to do is times all the numerator together, times all the denominator together, and divide it. That gives you your new pressure. So when you times 200 by 700 by 348, all together you have, yes, all that give you up together when you multiply all the numerator, 486,720 all over 350 times 298. 4, 3. Divide this by this. What we have is now your P2. What will that give you, class? Divide this by this.
0.
Please, you confirm it. 200 times 700 times 3 48. Please, you confirm your value.
7. 2
200, right? 00. So, this. So, 67.1 millimeter mercury. Now, what do you observe from the question? The first pressure of the gas was 700, and the second pressure is now 467, meaning that as the volume of the gas increases, the pressure of the gas decreases. So the question obeyed both the Boyle's law as well as the Charles law. That is very simple. Okay, the next thing I want to take question number 4. The question said that element will likely undergo what type of bonding or chemical combination. Now, before we were able to know the type of bonding such an element will likely undergo, first and foremost, we need to know what is the element that exhibits such electronic configuration, right? Now, solution. Your first S carry 2 electron, second S carry 2, second P carry 6, third S carry 2, and your third P carry 5, respectively. Now, to identify the elements, we're going to count the number of electrons that are there up together. Let's count. We have 2 plus 2 give us 4, plus 6 give us 10, plus 2 give us 12, plus 6 give us 17. So we identify the element as chlorine because it's having the total electronic configuration of 17. Now, if you remember what happened from the chemical bonding, we said because chlorine is electronegative element. What made chlorine electronegative element is because it ionized by gaining one valence electron. So the types of chemical bonding or combination the element will likely exhibit is electrovalence or the ionic bonding. Electrovalent is also known as the ionic bonding. So the element is chlorine, therefore it will exhibit electrovalent types of bonding or chemical combination. Because remember, if you have, for example, chlorine and sodium together, if you react there, during the bonding, this sodium lose electron, one electron, while chlorine gain one. So the element will identify it as chlorine and it's likely to exhibit electrovalent. Why does it exhibit electrovalent? Because it's only in electrovalent that LNX transfer electron from one shell to another, usually from metallic atom to non-metallic atom. This metallic atom that donates or transfer the electron, which we call them electron donor, and those electronegative that I said, they are also called the electron acceptor, respectively. Now, before we take our last question, I want to share us something very brief about what this man called above principle said as regards to the electrical configuration of any element. Now, how do you get the electrical configuration of an element given to us? Remember, it's very simple. Just use this method. First X, second X, third X, 4X, 5X, 6X, and 7X. Then next we have second P. Next we have third P, third D. Remember here, electrical configuration we have S, P, D, F. So after S, you have P, after P, you have D and F, respectively. So we are going to have 4P, 4D, and 4F. This is 5P, 5D, and you're going to have 6P, and then 7, respectively. Just follow that key. When you exert your first X, you enter your second X to this, to this, to this, to this, and finally this. So when you follow this principle, you can write the electronic configuration of any element without any stress. What is the key? First, start with your first X. When the block feed up, you enter second X. After second X, you go back to second P. Just follow your arrow. After second P, you enter third S. After third S, you are going back to third P. After third P, right 3 third D, you enter 4S before third D. Like that to infinity. So this is a principle that we normally use to find the electrical configuration of any element given to you. The last question that we are going to take asks us to find or to calculate the oxidation number of sulfur in the compound tetra also surface 6. What is the compound, or why is it called tetra also surface 6? Because of the oxidation number of the sulfur atom in the compound. How do we do or do we perform that? Remember, this is the last question for this class. Question 5. The compound is tetra also surface 6. And we have to find the oxidation number of sulfur in the compound. Very simple. Follow me. Now, hydrogen is having the oxidation number of 1 times it by the 2 here plus your sulfur. Oxygen is having a oxidation number of -2 times it with 4 will give us -8, and all will equals to 0 from the laws or rule of oxidation. Now, when we rearrange this, our sulfur will now be equals to, take -8 to the right, it gives us +8. When 2, because 2 times 1 is 2, when you take it to the right, it turns to -2. Therefore, your sulfur is equals to +6. And as such, we call this compound tetra also surface 6. Very simple. So that is how we find the individual element oxidation number in any given compound. For example, imagine you are asked to find carbonate calcium triiosocarbonate. How do you find calcium oxidation number of carbon and calcium triisocarbonates? Now, before I know whether it's carbonate 4 or carbonate 6, it's because of the help of the oxidation number of carbon in the compound. You must remember that calcium has oxidation number of 2. 2 plus 1 here will give you 2 plus your carbon. Oxygen is always -2 times here. You have -6. The rule of oxidation, your light find must be equal to 0. Collect your light 10, you arrange your 10. Your C turns to 6 -2. Therefore, carbon is equal to +4. So we can now give the IUPAC name to this compound as calcium triiosocarbonate 4. That is very simple. I wish you all the best. See you in the next series of video.